Our next speaker, we have Dr. Christine Hartzell. Dr. Hartzell is a professor of aerospace engineering at the University of Maryland, and she's going to talk with us today about lunar dust and plasma. Dr. Hartzell?
All right, thank you. So I feel like we've had a pretty good introduction to lunar dust in some of the other talks. So right now I'm going to talk about its interactions with the plasma environment near the surface of the moon. Let's go to the next slide. Okay, so in terms of motivation for understanding dust-plasma interactions on the lunar surface, there's really three stakeholders that we think of. So first, electrostatic dust motion is a process that may influence the evolution of the moon's surface, as well as the surface of other small airless bodies. So this is really a planetary science objective. We'd like to understand how bodies in the solar system evolve and if this phenomena occurs on other bodies. The second motivation for understanding these types of interactions is that they may influence our design of spacecraft. So we've heard about how dust deposition on spacecraft poses a hazard to long-term exploration of the moon. And several of the mitigation technologies being considered actually rely on electrostatic forces. So understanding these physics is really important for designing mitigation methods. And finally, the moon is a laboratory to investigate some of the fundamentals of dust-plasma interactions that we just can't replicate on the surface of the Earth. So it provides a unique environment to do some sorts of fundamental physics investigations as well. All right, so let's go to the next slide. Okay, so I'm going to walk through sort of the basic physics of dust-plasma interactions on the lunar surface. So if we have the lunar surface, it is immersed in the solar wind plasma. There's no atmosphere, and on a large scale, no real magnetic fields. If we just had the solar wind plasma interacting with the surface, we would tend to have a negative charge on that surface. But in addition to the solar wind, we also have solar UV radiation, which causes photoemission, and that tends to charge the surface positively. So on the day side of these bodies, we tend to get a net positive charge. Next. All right, so we have this net positive charge. Let's go next again. Now let's zoom in close to the surface. So we have a net positive charge across this lit surface, but when we zoom in to look at individual regolith particles, it actually gets even more complicated. So our regolith particles are dielectric, they're insulators. That means that we can have patches of positive and negative charge on individual grains. We can also have electrons that are emitted from one grain being deposited on a neighboring grain. And this has been hypothesized to lead to strong electric fields or repulsive electric fields between neighboring grains. And if that repulsion is significant enough, it can actually overcome gravity and cohesion and detach the particle from the surface. And this is the phenomenon that we call electrostatic lofting, this detachment of a particle from the surface due to the repulsion between neighboring grains. Next. All right, so we have this net positive charge surface in a plasma. It's going to attract electrons from the bulk solar wind plasma. So we have a region above the surface of the body that is called the plasma sheath. And this is a region where the electron density is greater than the ion density. Essentially, the plasma is shielding out that charge on the surface. And this charge differential in the plasma sheath gives rise to an electric field. And at least close to the surface, we think this electric field is pointing upwards. Next. Okay, so now we have our charged particle on the surface in the plasma. And if the electrostatic force is large enough to overcome gravity and cohesion, that particle could detach from the surface. Next. All right, now the particle could detach from the surface due to these electrostatic forces. That's what we're calling electrostatic lofting. But it could also detach from the surface due to micrometeorite bombardment or due to exploration activities. Say you have an astronaut walking on the surface, or you have a rover wheel that's kicking up dust. These activities can also detach particles from the surface. And regardless of the detachment mechanism, the particle is going to be charged. Now, if the particle is detached with just the right initial velocity and just the right initial charge, it may actually levitate. Next. So when I say levitation or electrostatic levitation, this is the idea that the particle could hover above the surface due to basically gravity and the electrostatic force on the particle canceling out. And the particle will translate over to a region of weaker electric field strength before it is redeposited back on the surface. Next. And this is all considering just your ambient, natural plasma dust environment near the surface. Things get a little bit more complicated when we stick a spacecraft into the system. So your spacecraft is going to be charged. It's existing in the plasma environment. It is also photo-emitting. So it has some charge, and that itself will modify the plasma environment. Additionally, the spacecraft's going to cast a shadow on the surface, preventing the shadowed region from photo-emitting. Again, will change the plasma environment. And finally, the presence of the spacecraft and any sorts of exploration activities may also change the regolith charge. So this is tribocharging that has been mentioned previously. Basically, if you have two regolith grains that roll over one another or collide with one another, they'll exchange charge. We call this static electricity in the terrestrial environment, but it's pretty difficult to dissipate that charge in the lunar environment. And so these factors associated with our spacecraft being on the surface also will change these dynamics of electrostatic lofting and levitation of particles. All right, so that's the basic physics of these phenomena. Let's go to the next slide. So what evidence do we have that electrostatic lofting or levitation actually occurs? Well, the first piece of evidence came from the Surveyor and Apollo era. So we had when these spacecraft went through local sunset, they observed a glow above the horizon that they thought was caused by light scattering off of small dust particles hovering above the surface. And this was called the lunar horizon glow. Then during Apollo 17, the LEAM instrument was placed on the lunar surface. And although it wasn't designed for this type of measurement, the results have been interpreted as the re-impact of dust particles of lunar origin. And they saw spikes in impacts on this sensor at sunset and sunrise. Then on the right side of the chart here, you can see an image not from the moon, but from the asteroid Eros. And on Eros, what we see is collections of small particles in the bottoms of craters. And it's been suggested that particles are electrostatically levitating and then being deposited in these craters. And most recently, the Chang'e 3 mission observed that there was a deposition of dust about 30 centimeters above the surface on rocks. So kind of a band of dust on these rocks, which is consistent with theories about electrostatic levitation. So we have all this sort of circumstantial evidence to indicate that electrostatics and dust are active on the surface of these airless bodies. But there's really no slam dunk evidence. There's no direct observations. So the LADEE LDEX instrument saw that there was no evidence of high altitude dust other than what was released by micrometeorite bombardment. And reanalysis of horizon glow observations has suggested that the horizon glow may actually just be zodiacal light. So there's still some controversy about whether or not these processes are active just naturally on the lunar surface, let alone whether or not they will be active when we introduce spacecraft and astronauts. Let's go to the next slide. There's been a lot of modeling and lab work to study these phenomena. So we have semi-analytical and computational models of the plasma sheath near the surface. On the right here, I'm showing the plasma sheath predicted around an entire asteroid cross-section. So this asteroid looks a little bit like a peanut, but we can see this, this model of what the electric field might look like about that asteroid. There's also been a lot of computational and experimental work looking at the question of the dust charge. And so this was a real big unknown for several years. And just recently, there's been a lot of progress to try to understand that small scale repulsive charging between individual grains. There's also been work looking at dust lofting feasibility, again, computational and experimental. On the bottom figure here, you see results from an experiment that very clearly show that dust is jumping from a pile up onto the side of this block in a vacuum chamber. So we do have experimental evidence that the lofting phenomenon is feasible. The question is, does it actually happen on the lunar surface? There's also been a lot of modeling work looking at the altitudes and sizes of particles that would levitate. There's been simulations of dust transported into craters on Eros. And we've also seen experimental electrostatic levitation. So both of these phenomena have been proven in the lab. We just don't have concrete evidence that they occur in situ. So let's go to the next slide. So here are a few open questions related to fundamental physics and planetary science of this dust-plasma interaction. So the first two are really concerned with the charge on dust particles. So what is the charge on a dust particle on a solid surface in a plasma? What is the charge on a dust particle in a bed of other particles in the plasma? This is testing that theory that we have about how electrons are transferred between neighboring grains on the surface of the moon. And then we get into sort of improving these models by looking at dependencies on particles' chemical composition and shape. So right now there's so much uncertainty in our models of charging that we really haven't done very much looking at how does a particle's chemistry and shape influence the charging or influence the lofting or levitation behavior. So these are really fundamental physics questions that could be answered on the lunar surface. From a planetary science perspective, we've made a lot of predictions about lofting and levitation that could be occurring on these airless bodies. Now it's time to bring some modern instruments to the lunar surface and test our hypotheses. So does electrostatic lofting occur on the moon? If so, when? What time of day? Where? Is there a specific altitude, latitude? Do we need to be in a crater? Do we need to be next to a rock? What are the conditions that lead to electrostatic lofting? And at what rate does this lofting occur? What size are the particles that are lofted? Is there a particular chemistry to those particles? And then similarly, the same sorts of questions with electrostatic levitation. What particles levitate? Where do they levitate? At what height do they levitate? What time of day do they levitate at? We really want to understand these phenomena and test the predictions that we've made, for the past 40 years on Earth. So yeah, these observations would test modeling predictions, and they would also inform spacecraft design. So now I'm going to transition to talking about the implications for spacecraft. Let's go to the next slide. All right, so when I think of lunar dust and plasma and spacecraft, I really think of an interrelated system because plasma influences the dust influences the spacecraft activities, the spacecraft influences the plasma because it's charged, right? All of these three concepts are connected, and we need to understand these dust plasma interactions in order to understand mitigation needs on the lunar surface and even understand different mitigation technologies. So let's go forward one slide. All right, so what is the rate of dust accumulation on spacecraft? If electrostatic lofting and levitation happen, which particles are moving, and are they attracted to our spacecraft due to the shadowing of the spacecraft? Is this a bigger hazard at certain times of day or at certain landing locations, be that at a near polar region or if we're near a crater, right? What are the impacts of these variables on the rate of dust accumulation via this mechanism? The next big unknown is how is dust accumulation influenced by tribocharging? Basically, any activity that your spacecraft participates in on the surface is going to cause tribocharging. If you charge up the grains more, is that going to increase your rate of electrostatic lofting? And will those lofted particles end up accumulated on your spacecraft? Or will they end up being levitated? These are things we'd like to know. And then how will the spacecraft charge? There's going to be a variation with time of day and landing location. And how does the charge of the spacecraft influence the plasma sheath? Let's go to the next slide. This is also relevant to mitigation. So several of the mitigation technologies that are being considered rely on electrostatic forces. On the right side of the chart, on the top right, I'm showing images of the electrodynamic dust shield that's been developed at the Kennedy Space Center. And what this is it's basically a series of concentric electrodes, and they run a wave through these electrodes, and they cause electrostatic lofting, right? The particles sitting on the electrodes are repelled and they hop off the electrodes. So you're seeing a before and after picture there on the top. So this relies on the charging of the particles. It also relies on, or it also will influence the plasma environment, right? If we have a traveling wave moving across the surface, the plasma is going to respond to that electric field that's generated. Additionally, on the bottom of this slide, you can see another technology that's being developed at the University of Colorado that involves shining an electron beam on a surface, basically increasing the charging of those particles, again causing electrostatic lofting and these particles to hop off the surface. So both of these methods are dependent on understanding the charging of the particles, and both of these methods are going to change the local plasma environment. So we would really like to understand the plasma environment and be able to predict particle charging in order to optimize the design of these mitigation technologies. So let's go to the next slide. Okay, so in conclusion here, the dust plasma spacecraft system is an interconnected system, and it's really ripe for experimental investigation. There's been a lot of computational and experimental work making predictions about what the environment is like on the surface of the moon. It's a less mature field when we start throwing the spacecraft into the mix, but we need spacecraft on the surface in order to make these measurements. So I think it's time to place some modern measurements on the surface of the moon, or modern instruments on the surface of the moon that can inform these investigations. And there's a number of outstanding fundamental physics and planetary science questions that could be investigated to test our theories. And then finally, dust plasma interactions are relevant to spacecraft operations, especially mitigation. You know, mitigation technologies are sensitive to the charge on dust particles. So predicting that charge would really be helpful in order to design some of these technologies. And with that, I'm happy to take any questions.
Thank you, Dr. Hartzell. What a fantastic talk, and bringing up a new area for us to be really thinking about that's going to be important in the future here. We do have time for one or two questions. So the first one is: the plasma crystal experiment on the International Space Station a good test bed for verifying electrostatic lofting on the moon?
So on the ISS, like, there are some great facilities that we can use to understand the fundamental physics of dusty plasmas or dust in plasmas. I'm not very familiar with the instrument that you're referring to, but we have seen electrostatic lofting in the lab on Earth. We'd need at least a partial gravity environment in order to look at lofting on the ISS, and I'm not sure if they have that capability.
Okay. Next question. What is the depth extent of surface material thought to participate in the dust lifting phenomenon?
So right now we're thinking that it's just that very upper layer of regolith, because our understanding of the charging model currently is that we need to have a particle being hit by some UV radiation from the sun, emitting an electron. That electron gets captured by a neighboring particle, and then that neighboring particle, is repelled from its surrounding grains, and that particle moves. So really, this would just be the upper layer of regolith. Now, it may be something where the upper layer of regolith moves, and then the layer below it is able to move again, right? We're not really sure how deep this phenomenon would go, but it would only be active for very small particles, so like micron scale particles on the lunar surface. So anytime you get particles that are larger than that, this phenomenon would not be strong enough for that to occur, unless you have some other complicating factor, like you're shooting an electron beam at it, so you're really charging things up, or you've somehow modified the plasma environment to make it much stronger. But just naturally, we would think only like micron scale particles and only the top layer of particles.
Okay. And one last question. Are there any plans to do a DTO on the first crewed Artemis mission to prove out the electrodynamic dust shield technology?
I'm not sure what a DTO is.
I'm not either.
I'm demonstrated technology option, something
Design
maybe?
test objective.
Okay. Okay.
Okay.
It is just an
Thank you.
experiment. Yes.
I don't know of any plans to fly the electrodynamic dust shield to the
Mhm.
lunar surface, but I may
I
be
think there
incorrect on that.
is. I think one of the COTS landers, or I mean, Eclipse landers has a demo, electrostatic repulsion demo on it. I'll have
Okay,
to
that's great.
look in
That's
my
great.
my list.
Great. I'm sure you'll be very interested in the results from that.
Yeah, definitely.
All right. Well, thank you again, Dr. Hartzell and Jerry. I believe you're up next. So, in perfect timing and tying into this.